Welcome to the Introduction to Geographic Information Systems and Science lecture series developed by the Quinney College of Natural Resources at Utah State University. Discussion topics for this lecture include data query, spatial queries and attribute queries, or select by location and select by attribute, Boolean operators, and data conversion. Data query is known as statements or logical expressions that are used to select features or records from a feature dataset or a raster dataset or from an associated table. A spatial query is conducted to select geographic features based on a spatial relation of one feature to another. Attribute queries are conducted to select features from a feature dataset based on a specific attribute type. A spatial query is a statement or a logical expression that selects geographic features based on location or a spatial relationship. As an example, we'd like to identify those trees that occur within 20 meters of a riparian area and restrict those trees from being harvested during a timber harvest operation. Based on the 20-meter buffer around our riparian area, we can then select those points that fall within that buffer and identify those trees as no-harvest trees. Another example of a spatial query is a spatial query whereby you would select polygon features that have some topological relationship to one another. In this case, we may like to select features that are adjacent to each other, such as where polygon A and polygon B are adjacent, but not to polygon C or polygon D. In this case, the GIS would show us these areas between polygon A and polygon B that meet our criteria or our spatial query. Many spatial queries depend on the topological relationships between spatial features. Attribute queries are conducted by developing a query statement that identifies records of features in a table based on some attribute value. For example, you've acquired a land ownership GIS data layer for the state of Utah and would like to identify lands that are administered by the BLM or DoD. In this case, one could go through the table and identify each record individually, or one could conduct a query that would use the GIS to select those features of interest. Jumping into ArcGIS, we have such a data layer here. You can see this data, downloaded from the State of Utah AGRC, contains information concerning land ownership of the entire state. At the bottom of the screen, you can see the attribute table, and each one of these attributes contain a series of information about different polygons, including the agency, the ownership of the land administrator, and so on. Rather than going through this table and selecting all these records by hand, we would like to conduct an attribute query that would select those records for us. In our selection drop-down option in ArcMap, we're going to choose the option Select by Attributes. So note we have our land ownership layer selected here. In this window, you can see all of the attribute column fields that we have the options to choose from. In this case, we've identified we would like to find those lands administered by the BLM or the DoD. We'll double click on Admin, and then we have a series of operators here that allow us to build our query. In previous math classes, you may recognize that some of these appear to be Boolean operators, and in fact they are. In this case, we would like to select admin that is equal to BLM, but we'd also like to select those features or those records that are also associated with the DoD. In this case, we don't want to use an AND because we're not looking at where both BLM and DoD would administer the lands, but rather where one or the other is the administrator. So now you can see in this window our Select by Attribute query has been built, where admin equals BLM or admin equals DoD. Within ArcGIS, we can verify this. The expression was successfully verified, and we can apply the expression. Once the expression is applied, we can come back to ArcGIS, we can zoom out, and we can see all those lands or features that have met the requirements of the spatial query. Additionally, we can look inside of our table and find all of those records that have been identified. If you note here, there are 2,217 out of 12,657 records selected, a much faster process than conducting it by hand. As we mentioned a moment ago in ArcGIS, we had Boolean operators that were available for us to use and build our queries. George Boole, who lived from 1815 to 1864, invented the concept of what we know as Boolean logic, which is a mathematical expression that results in a true or false condition. Whether you know it or not, you've often used Boolean logic to conduct many different types of analyses problems in schoolwork, professional work, or research. Boolean operators can generally be summed up by the four you see on the screen: and, or, not, and XOR. These logical operators can be joined together or used independently to conduct different types of queries. So in this example, we're looking at the Boolean operator AND. We would like to identify in the two circles where A and B must be true. So if we think about where A and B must be true, we would identify that it's those two places where A and B overlap one another. Concerning the OR operator, we'd like to conduct the query where circle A or circle B must be true. In this case, since it's circle A or circle B, and we're not defining anything about where the overlap happens to occur, both circles would be selected. Concerning the NOT operator, where circle A but not circle B must be true, we'd identify that circle A only would be selected, leaving circle B and the overlap areas unselected. And finally, the operator XOR, where A or B may be true, but not A and B. This means that we're going to have a hole in the middle where the two overlapping polygons exist. So A or B may be true, but not both A and B. So consider this. We have a feature data set that contains tree locations. Each point is attributed with tree height and trunk diameter. We're interested in all trees greater than 20 meters tall and with a DBH, or a diameter at breast height, greater than or equal to 100 centimeters. What would your query look like? Well, a simple query for the statement would be height greater than 20 and diameter greater than or equal to 100. Notice that we use the AND Boolean operator to locate features where both height greater than 20 and diameter greater than or equal to 100 were true. Moving on and switching gears a bit, discussion about data conversion is important when using GIS. It is possible to convert vector data to raster data formats and raster data to vector data. One needs to note that care should be taken to avoid misrepresentation of spatial and non-spatial information when conducting these data conversions. A discussion of data conversion requires us to review raster data models. Remember that raster data represent a geospatial feature or features or phenomenon through a series of grid cells or pixels. Each pixel represents a spatial location on the surface of the Earth, and every cell or pixel in the raster has a unique value. This is important when we're talking about data conversion because cell size becomes an issue. When discussing cell size and a brief segue into raster resolution, often you'll hear the comment, "What is the raster resolution of your data set?" So it's important to identify how you can tell what the raster resolution of a data set truly is. This will impact your data conversion operation. There are three ways to identify what the resolution is of a raster data set. 1. Individual or organization that provided the data to you provides that information verbally. 2. You use the measuring tool in ArcGIS to measure the length of the side of a pixel. 3. You use the layer properties window to identify what the actual cell size is. The third option is the most reliable and standard way of identifying a cell size. Moving into ArcGIS briefly, here on the screen we can see a raster data set, a digital elevation model for central Utah. If we right-click and choose our Layer Properties window, we can look within the Layer Properties Source tab to see that the cell size, XY value of each grid cell, is 10 by 10 meters. Data are fine-scaled if they include more records of small objects or high spatial resolution, and data are considered coarse-scaled if they include fewer records of larger objects or low spatial resolution. In the aerial photo on the right side of the screen of the Utah State University campus taken in 2009, you can see this is a half-meter pixel resolution data set of the USU campus. We can step through this data and resample it and show how changing pixel size impacts our resolution and coarseness of data. This is a 1 meter data set. This is a 2 meter data set. This is a 5 meter data set. This is a 30 meter data set. And this is a 250 meter data set. Each one of these pixel resolutions has some value, but possibly not at the scale of this image. Once we reach the 250 meter pixel resolution, we lost all definition of the ground detail When you're conducting data conversion, especially vector to raster, you have to remember that you're going to lose the explicit edge of a vector data set. So as you can see in the example from the Jensen and Jensen book on your screen, we have a vector to raster conversion of interstate, state, and paved local roads along the Wasatch Front in Utah. This is a vector road network, and we're going to take that vector road network and we're going to rasterize it. Now it might be slightly hard to see, but if you take the vector network and change it to a 250 meter pixel resolution data set, you can start to see that we lose that definition and we no longer have a true width of the road. Granted, there was not a true width necessarily with a discrete line feature, but it was slightly more accurate with respect to the spatial location of the road. Taking that data set even one step further to a 500 meter pixel resolution, you can see how we lose detail and we now have a coarse representation of our road network. Likewise, you can take raster data and convert it to vector data. However, this is where the discussion of raster cell size really comes into play. You want to make sure that if you're converting this data from raster to vector, that you're doing so using the proper cell size, and creating a spatial data set from a gridded data source will suit your needs. So converting raster to vector, taking the raster data from the Utah Vegetation Gap Program and converting that into a vector format. You can see that we have many individual pixels, now identified as very small polygons. We have very jagged edges. This may or may not suit the needs of your vector data set requirements.